Satellite telecommunications rely heavily on radio frequency transmission, but increasing the data rate across these vast distances requires pushing more and more power through an already dissipating wide-angle radio wave. An antenna's data transmission rate is physically constrained by its beam width. As a radio beam spreads out, its gain drops, and the signal dilutes before it ever reaches the receiver. Free-space optical communication bypasses this limit by operating at much shorter wavelengths. By using a highly collimated laser beam, the signal maintains its density over the same distance, allowing us to increase the available data rate by at least a full order of magnitude using the exact same amount of transmitted power. Because the beam is so tightly focused, it is extremely difficult to intercept, granting high data security. It also falls completely outside of heavily regulated radio frequency bands. But to achieve these aerospace engineering improvements, we have to look away from traditional radio antennas and examine the quantum mechanics of solid-state optoelectronics. The core engine at both ends of a photonic data link is the semiconductor PN junction. On the transmitter side, applying a forward bias voltage to the junction forces the injection of minority charge carriers. Electrons and holes recombine across the boundary, releasing energy in the form of light. The receiver operates in exact reverse. By applying a heavily reverse-biased voltage, incoming photons are absorbed to trigger impact ionization, breaking atomic bonds to release a cascade of electrons. Building a functional optical link requires mastering this physical symmetry, maximizing light extraction at the emitter, isolating single photons at the receiver. Generating that light is a process called electroluminescence. When electrons drop from the higher energy conduction band to the lower energy valence band, they release a quantum of electromagnetic energy. The physical energy difference between those two bands, the band gap, dictates the precise wavelength of the emitted photon. This recombination is not instantaneous. There is a slight time delay, known as the minority carrier lifetime. For the diode to produce light, this radiative process must happen faster than non-radiative recombination, where carriers are trapped by microscopic defects in the crystal lattice and lost as heat. This dual energy band diagram compares the structure of two types of semiconductors. It plots energy on the vertical axis against momentum on the horizontal. In indirect materials like silicon carbide, the lowest energy valley of the conduction band does not align with the highest peak of the valence band. An electron must shift its momentum before it can recombine with a hole, resulting in a prolonged radiative lifetime. Direct gap materials like gallium nitride have their energy states perfectly aligned. Recombination happens immediately, yielding an internal quantum efficiency as high as 12%, compared to silicon carbide's fraction of a percent. Because of this alignment constraint, generating photons effectively requires selecting specific direct bandgap compounds to ensure radiative emission dominates the system. Generating light inside the semiconductor is only the first hurdle. The actual bottleneck is extracting that light out of the chip and into free space. Inside a standard cubic semiconductor, light generation is isotropic, meaning photons radiate outward in all directions equally. According to Snell's law, a photon can only pass from a high refractive index medium to a lower one if it hits the boundary at a shallow enough angle. This defines an escape cone at the surface. Light rays that intersect the surface at angles less than the critical angle exit the chip and travel into the surrounding environment. Rays hitting the boundary at wider angles undergo total internal reflection. They bounce off the inside of the surface and stay trapped inside the semiconductor. In standard diode designs, these trapped photons are absorbed by the underlying substrate. Up to 98% of generated light is wasted as internal heat. To increase optical output, engineers implement transparent substrates or layer-graded refractive indexes to physically widen the escape cone, allowing more photons to successfully cross into free space. Once the light escapes, it has to survive the journey. A transmitted photon will cross hundreds or thousands of kilometers of free space before striking the crystalline surface of the receiver. Over these immense distances, the tightly collimated beam still attenuates. By the time the signal reaches the detector, it consists of incredibly faint individual photons. Standard PIN photodiodes convert one photon into one electron. At this extreme range, that tiny electrical current is completely drowned out by the ambient thermal noise generated by the system's own secondary amplifiers. To isolate the signal, the receiver uses an avalanche photodiode, or APD, operating under a massive reverse bias voltage. The internal architecture of an APD separates the semiconductor into two distinct zones. A photon enters the absorption region and generates a single electron hole pair. That electron is then swept downward into a high electric field multiplication region. Because of the high reverse bias potential, the electron is violently accelerated. It strikes the crystal lattice with enough kinetic energy to knock loose additional electron hole pairs, a process called impact ionization. Those new carriers are also accelerated, triggering more collisions. The initial single photon exponentially multiplies into an avalanche of thousands of charge carriers. Operating the diode just below its breakdown voltage ensures this avalanche eventually dies out to friction, providing a measurable pulse for every detected photon. The resulting electrical current is a product of the spectral responsivity, the incoming optical power, and a crucial internal gain factor denoted as M. By manipulating the voltage to drive up this internal gain, an APD mechanically lifts a faint optical pulse high above the electronic noise floor, preserving the data stream. This entire link, from emission to multiplication, only functions if the transmitter's band gap wavelength aligns exactly with the detector's peak spectral responsivity. Silicon-based avalanche photodiodes possess excellent excess noise factors, but they are physically blind to wavelengths beyond 1100 nanometers. Atmospheric LiDAR systems leverage this by pairing a 905 nanometer pulsed laser diode with a matching silicon receiver. High-speed telecommunications and free-space optics, however, demand the 1550 nanometer wavelength to reduce atmospheric absorption and maintain eye safety. This chart plots wavelength against material responsivity. To operate at 1550 nanometers, engineers must use indium gallium arsenide for both the transmitter and the low-noise receiver. The emission spectrum curve of the transmitter must perfectly overlap with the detection curve of the receiver. This precise spectral alignment allows indium gallium arsenide systems to support continuous data transfer rates of up to 12.5 gigabits per second over long distances. Creating a viable signal-to-noise ratio across hundreds of kilometers of empty space relies entirely on the precise matching of epitaxial compound materials. The optical link is a closed loop of mirrored physics. The transmitting node's forward bias forces charge recombination, emitting energy. The receiving node's reverse bias forces impact ionization, absorbing it. The entire architecture takes the exact same solid-state structure and drives it in opposite directions. Tuning the band gap of the crystal and refining the epitaxial layers solves the extraction efficiency bottleneck on the satellite and overcomes the amplifier noise problem at the ground station. These microscopic physical properties have immediate consequences for how we build and deploy hardware in space. Private, commercial, and scientific activities now require a faster and more affordable infrastructure than traditional radio-based networks can provide. Because optical components are built at the solid-state level, they can be integrated into small, standardized formats like CubeSats, replacing bulky radio dishes with terminals that fit in the palm of a hand. Scaling global data networks into orbit ultimately comes down to our ability to manipulate the quantum states within these compound semiconductors.